Okay, hi everyone. This is a video recorded for the Junior Mathematician Research Archive. My name is Elisa Bellah. I'm a graduate student at the University of Oregon. I'll be talking about norm form equations and linear divisibility sequences. So to start, let me give you a bit of background. So let's let K be a number field and W any Q linearly independent subset of K. With this, I'll define the norm form associated to the set W to be the rational form, defined by taking the norm of linear combinations of elements in the set W. You can show that this is, in fact, a rational form. And so you can pose this Diophantine problem of finding all integer solutions to equations of this type. Okay, so let me give you a couple of examples to show you that this is likely familiar. So first of all, let's consider this Pell equation, x squared minus dy squared is equal to c. Observe that you can factor on the left-hand side of this equation to rewrite this as the norm of elements x plus y squared of d over the number field q adjoint squared of d. And so this is a norm form with defining set 1 squared of d. Okay, so every Pell equation is a norm form equation. Another example, if you have some number field k and say you found an integral basis w for k, then solutions to these two norm form equations, where your value for c here is plus or minus 1, give you all of the units in the ring of integers. Okay, so I want to talk about very briefly about this classic characterization of solutions to norm form equations. So the way that you do this is you take your norm form f sub w and you associate to it a z module generated by the set w. So let me call that module m. And then my characterization will happen over here in the world of modules. But if I want to do that, if I want to work with a module abstractly, I can't have the basis fixed. So what happens if I change my basis? Say I have some other basis t. The associated norm form, these two are not necessarily equal, but it's a short exercise to show that they are integrally equivalent. And so up to integral equivalency, which is really what you want for Diophantine problems, every norm form is associated to a unique module in your number field K. Okay, and so what that means is solutions to norm form equations can instead be obtained by finding elements in the associated module of fixed norm C. So for the rest of this talk, for most of the rest of this talk, we'll just be talking about elements in modules of fixed norm. Okay, so here's how this characterization goes. So I'll talk about the characterization for full modules, meaning that the rank of the module is the degree of the number field. But I'll note that there is a similar characterization in the non-full case. It's a bit more tricky, but this was mostly covered by Schmidt. Okay, so given a full module, I'm going to define O sub m to be the coefficient ring of my module. So these are the elements in my number field, so that when I multiply by anything in my module, I stay in my module. And with that, I'll denote plus, I'll let that denote the positive unit group of my module. So these are the elements in my coefficient ring with norm equal to 1, and so these elements are units. Okay, and so this very classic fact is that all elements in a full module of fixed norm lie in finitely many disjoint families of this type. Okay, another fact that's not too hard to show is that when your module is full, the coefficient ring is an order in your number field. So Dirichlet's unit theorem applies in this setting, and you get that the positive unit group is a finitely generated abelian group. Okay, so what is this characterization actually telling you? This is telling you that our Diophantine problem of finding solutions to norm form equations can be solved if we have two things. So first of all, an algorithm to compute this finite list of non-associate elements of fixed norm in your module. And then secondly, an algorithm to compute a basis for the free part of your positive unit group. And so In theory, this problem is solved. There are effective algorithms for 1 and 2, but generally these are not computationally feasible. These are not things that you reasonably would be able to run and hand back answers. Okay, so we need to do something different if we want to understand explicit information about norm form equations. Okay, so one thing I do want to point out is that this characterization tells us that we can generate infinite sequences of elements in my module of fixed norm C by fixing an element and multiplying by units in the free part of my positive unit group. So let me just say that again. If you have some fixed element in your module with the norm that you want, and you take an element in the free part of the positive unit group, then I'll let alpha k be this sequence of elements, beta times epsilon to the k. This gives you an infinite sequence of elements in your module of fixed norm C. This follows by choice of epsilon being in the free part of the positive unit group. Okay, so if we let W be a basis for my module, and I write these, this sequence of elements alpha k in terms of this basis, going back to my Diophantine problem, remember this says that I get infinitely many tuples of solutions to my original norm form equation. Okay, so these integer sequences, xi of k, is what I would like to focus on for this talk. So let's give them a name. Let's call them the coordinate sequences of alpha k, and they change depending on basis. So with respect to the basis of my module. Okay, so my question is, without finding these elements beta or epsilon explicitly, which we saw in the previous slide is quite challenging, is there anything that we can say about these coordinate sequences? And the answer is you can say, or at least what I can say in general is one thing. And then the majority of this talk will be focusing on results in particular cases. So what we can say in general is if you have some unit with minimal polynomial of this form, then the coordinate sequences of alpha k from the previous slide satisfy this linear recurrence, where the recurrence relation can be read off if you know the coefficients of the minimal polynomial of your unit. And furthermore, if the degree of your unit is the degree of the number field, then this recurrence is actually minimal. So this lemma sort of tells you two nice things. First of all, it tells you that all of these coordinate sequences are linear recurrent sequences, and they all satisfy the same recurrence. And secondly, when the degree of the unit is big enough, then it tells you the order of the recurrence. Okay, so the idea for this proof, I won't say much about it, but the main idea is to use the non-degeneracy of the trace pairing to write each of these coordinate sequences as traces of some fixed element gamma times these powers of your unit epsilon. And then you use like the linearity of trace to show that your coordinate sequences satisfy the recursion that you want. Okay, so that's sort of how that proof goes. I want to make an observation here is that these coordinate sequences all satisfy the same recurrence. And moreover, that recurrence is independent of the choice of basis for my module. If I change my basis, I should get different sequences. So what actually changes, changing the basis just changes the initial conditions for my sequences. So this is a fact I'll use throughout the rest of the talk. Okay, so great, that's all that I can say in general. So I'd like to focus now on norm forms in particular fields, so real quadratic and certain quartic fields. Okay, so in the real quadratic case, so let's let K be a real quadratic field and M some full module in K. Suppose that we have some element in my module, a unit in the free part of my positive unit group, and just like before, form this sequence of elements alpha K to be beta epsilon to the K. Then the key lemma from before says that the coordinate sequences of alpha k are all order 2 linear homogeneous recurrent sequences. So this turns out to be nice because we know quite a bit about order 2 recurrent sequences. So let me just tell you the background that we need in a quick aside. So I'll come back to that slide in a second. So let me just give a quick definition of Lucas sequences. So if you have non-zero coprime integers p and q, I'll define the Lucas sequence with integer parameters pq to be this order 2 linear recurrence sequence, initializing at 0, 1, and with this order 2 recurrence written here. So just to tell you, this is familiar, the Fibonacci sequence is a Lucas sequence with parameters 1, negative 1. So you can think of Lucas sequences as sort of generalized Fibonacci sequences, if you like. Okay, so a really nice fact is that every Lucas sequence satisfies this divisibility property. So the property is that if the indices of your sequence divide each other, then so do the terms of the sequence. I'll give this a name. So sequences with this property that are linear are called linear divisibility sequences, which I'll often just abbreviate by LDS. And this property turns out to be really nice. So I'll just say divisibility sequences have been widely studied, primarily because they have just very nice factorization properties. And so if I'm interested in studying maybe like the arithmetic of these coordinate sequences, this would be a really nice starting property to have. So my question is, can I find a basis for my module so that my coordinate sequences are linear divisibility sequences? Okay, and the answer in the quadratic case, so this is just a copy of the slide we had from before, the answer is always yes. So I'll write this as a proposition because its proof is pretty short. The proposition is that there exists a choice of basis for my module, so that if I write my solution sequence in terms of this basis, then the first coordinate sequence is a linear divisibility sequence. Okay, so the proof is to just construct a basis for your module, which we do explicitly in this paper, so that the zero value is equal to 0. And then you can show that this first coordinate sequence is just a non-zero multiple of a Lucas sequence. And from our previous slide, this tells us that this first coordinate sequence is LDS. Okay, so that's the proof of that proposition. I want to make a remark here because it would have been nice if I could find a basis so that both of these coordinate sequences were linear divisibility sequences simultaneously. Unfortunately, this can never happen for the following reason. So there's this proposition, I found it by He and Xu, its earliest version in 2009, that an order 2 linear homogeneous recurrence sequence is a linear divisibility sequence if and only if its zero value is equal to 0. So the trouble here is that if you wanted both of these x1 of k and x2 of k to be linear divisibility sequences, their zero values would need to both be equal to 0. But then that would mean that beta would be equal to 0. And so alpha k would be identically the 0 sequence. So unless you're studying identically the 0 sequence, then your coordinate sequences in the real quadratic case cannot simultaneously be linear divisibility sequences. I need to choose a new basis for each coordinate. So that's just the remark I wanted to make there. Okay, so my question then is, does this result that I had in the real quadratic case, this result where I can find a basis for my module making one of the coordinate sequences an LDS, does this hold in any other cases? Or is this just really special about the fact that Lucas sequences were popping up here? Okay, the answer to the question is yes. This does hold in other cases, and we'll give 2 families of examples, both in quartic number fields. Okay, so let me give the setting. Okay, this picture is just describing this sentence. So let's let K be a quartic field with real quadratic subfield L, so that K contains a quartic unit, let's say square root of epsilon, where epsilon is a unit in the real quadratic subfield of positive norm. Okay, so that you know this isn't completely contrived, there's this proposition by Kuroda that says there are infinitely many such fields. They arise as biquadratic fields. Okay, so now let's do the usual thing. Let's take a fixed element in my module. Let's let alpha k be beta times my unit square root of epsilon to the k. And then in this case, you can compute what the conjugates of square root of epsilon need to look like. And using this and your key lemma, you can find that the coordinate sequences all satisfy this recurrence. And furthermore, since I assumed that square root of epsilon was of degree 4, this recurrence is minimal. So this is saying that my coordinate sequences of alpha k are all order 4 linear recurrence sequences with this recurrence here. Okay, so right, my recurrence isn't going to change, it's fixed. What I can change is my initial conditions. So sort of the first question is, what initial conditions, if any, would make this a linear divisibility sequence? And I'll just write that in a separate lemma. So suppose that you had some order 4 linear recurrence with the same recurrence from the previous page, and initial conditions that I've written here in red. Then we can show that this sequence is a linear divisibility sequence. So I won't go into the details of this proof, but just the idea is to show that in the even case, your sequence is just equal to a Lucas sequence. This part isn't surprising because if you look at the recurrence, you can see that you have an order 2 subsequence sort of sitting inside of there, and it's initializing at 0. And then in the odd case, with a little bit of work, you can show that this is actually a sum of 2 consecutive terms in the Lucas sequence, where this is a Lucas sequence with parameters t and 1. And then you can use various Lucas sequence identities to show that this satisfies the divisibility properties that you want. Okay, so we found an example with recurrence and some initial conditions that work out. So this lemma is going to lead to my 2 families of examples. Okay, so for my first family, suppose that I have the setting from before, some quartic number field. Then my first theorem is that if you take any element in your number field k and write alpha k as usual, then there is a choice of basis for this particular module, beta times the adjoint square root of epsilon, so that if you write alpha of k in terms of this basis, then the first coordinate sequence is the linear divisibility sequence. I'll show you the proof to this in a second, but just a quick remark similar to before. Since we know our coordinate sequences satisfy this recurrence here, we can argue, right, I guess, so the thing to note is that you have this order 2 linear recurrence subsequence sitting inside of it. And so you can argue, just as in the quadratic case, that if you wanted to make all of your coordinate sequences linear divisibility sequences simultaneously, that would force alpha k to be the 0 sequence, which is not what we want to think about. It's not very interesting. So my theorem says that you can do one at a time. Okay, so let me give you the proof of this theorem. It's actually pretty short once you have the lemma from the previous slide. So let me note a couple of things first. So note first of all that every term in this sequence, alpha k, all of these elements are actually in this module beta times the adjoint square root of epsilon. Otherwise, this would not be a very good choice of module. And also note that this module has a particularly nice basis. This is why we chose this module. Okay, by the previous lemma, recall all we need to do, we know that our coordinate sequences satisfy the recurrence we want. We need them to we need the first coordinate sequence to satisfy the initial conditions in the first column of this matrix A. So it suffices to just show that this equality holds, because over here on the right-hand side, note that this is alpha of 0, alpha of 1, and so on. So these are the initial conditions of alpha k. And so here, this first column is the initial conditions of my first coordinate sequence. The reason this result is so easy to show is that this vector of initial conditions for alpha k is also a basis for this module. So all you need to do is you need to fill in this matrix A of initial conditions for my coordinate sequences to be a GL4Z matrix. And I'll just tell you what you can do explicitly. Here's a GL4Z matrix doing what we want. Okay, so that's the proof of that theorem. There's actually something sort of nice that comes out of this just by chance as well. If you let W be the basis constructed in the previous slide, so constructed by taking A like this, then we can show that, so we just showed that the first coordinate sequence is a linear divisibility sequence. I've highlighted that in blue here. But also we can show that all of the other coordinate sequences alternate between 0 and a term in a Lucas sequence. And actually there's sort of a nice symmetry if you look at the table where there's sort of this symmetry along the diagonals. Right, so we can show something about all of the coordinate sequences simultaneously here, which is nice. Okay, so for the second family of examples, I'm going to look at a particular quartic number field satisfying the conditions that I had before. So let's let K be Q adjoint square root of M square root of N, where M and N are positive non-square, and N is 1 more than M. So you could do things like Q adjoint square root of 2 square root of 3, or Q adjoint square root of 5 square root of 6, and so on. Then the second theorem says, if you consider this full module, C adjoint square root of M square root of N in K, then this element eta is a unit in the positive unit group of this module of the form that we wanted. And moreover, there is a basis for this module so that if I write the powers of this unit eta in terms of this basis, the first coordinate sequence is a linear divisibility sequence. Okay, so I'll just say as a note, the first like half of this theorem is fairly straightforward. Just the fact that eta being square root of M plus square root of N is a unit in the positive unit group of the form that we want. This can just be verified by a quick computation with epsilon in this form written here. So actually finding this basis turns out to be more challenging than in theorem 1. I'll give you the idea just to show you where the challenge comes up. So just like before, it suffices to find a basis for our module so that the first coordinate sequence has the initial conditions that we want. And so we'll set up this equality just like before, right? This vector over here on the right-hand side gives you the initial conditions of alpha. So these are the initial conditions of the first coordinate sequence with respect to this basis. The trouble here is that my module is no longer just equal to Z adjoint square root of epsilon. So this is no longer a basis, which means it no longer suffices to just fill in A to be GL4Z. So what do? We use the fact that Z adjoint square root of epsilon sort of sits nicely inside of this module. So its quotient is 2 copies of Z mod 2Z. And then we use a little bit of geometry of numbers, just this fact that you can lift primitive lattice elements to a basis. And then in this paper, we give sort of an algorithm to construct the basis, and I've just constructed it explicitly here. And so just to remind you, what this says is if you write alpha k in terms of this basis listed here, the first coordinate sequence will be a linear divisibility sequence. Okay, so I'll stop there. Thank you so much for listening. If you have any questions, feel free to email me at any point. I listed my email here, but it should also be listed in the description of this video.